Hello, everyone. Today I'm going to show you how to go from the Navier-Stokes equations to the famous solution of called Hagen-Poiseuille flow. So this is the version of the Navier-Stokes equations where we have a so-called incompressible flow. This is the equation coming from that particular assumption, whereas this one here is just the conservation of linear momentum, which is somewhat a generalization of Newton's second law. This is a little bit different to what usually is on the books. This is the usual term that you have for the convex, it's called transport term. But as we will see next in a different video, this is a different, this is the right way in which this term should be written at all times. Whereas on the right-hand side, we'll take the two terms of the, generally speaking, three terms that we have in this type of problems, namely the viscosity associated term, the pressure term, and this is the one associated with so-called body forces, which typically come from the weight of the material we're considering. If we want to represent this motion in some sense, we'll see this as the flow of a fluid, a Newtonian fluid, across a pipe whose cross-sectional area is a circle, as we see here. If we look at this flow from a section view, as we see here, you'll see that the flow looks like a parabolic profile, give or take, where the velocity is 0 on the walls of the pipe, and it gets to a maximum precisely at the center line of the pipe. So to solve this problem, we will we'll find how the Navier-Stokes equations look like in terms of cylindrical coordinates. So to start with the calculations, we need to get some assumptions in place. The typical assumptions are that the flow is steady, essentially no dependence in temperature. Another typical assumption is that this is an axial flow problem, meaning that out of the three components on the radial direction, the tangential direction, and the axial direction, the only one which is not 0 is precisely the axial direction term. And on top of that, we will assume that this axial velocity term depends only on the radial variable, meaning that we will not take into account any dependence on the position along the axis or the position along the angle on the cylinder, okay? But making those assumptions means that we are ruling out any kind of swirling, or some people also say that this is the axisymmetrical flow assumption. So as I said before, we will work on cylindrical coordinates. So in cylindrical coordinates, this is the form that the gradient of velocity and the Laplacian of the velocity look like. And also here we have the pressure gradient, as you can see. Enforcing all these assumptions we just mentioned imply that every single term with both either the radial component or the tangential component of velocity appear, every single one of them will be 0. So all of this just goes away. Okay, nothing of those terms will appear. This one is a derivative of this axial direction component with respect to the radius, so that one stays. As for the other ones, are all of them 0. Okay, so in a sense, all that we end up with is precisely a matrix whose only non-zero component is this, whereas everything else will be filled with zeros. All right? In a similar way, if we go to the Laplacian of the velocity term, this is also 0. All the BR and B theta terms are 0. As we can see here, none of them are non-zeros. And on the last one, this is also 0 because the axisymmetrical flow assumptions. This is also 0. So in the end, the only non-zero terms to be the second derivative here, the second derivative of z with respect to r plus 1 over r, the first derivative with respect to r, right? Then we will see how the nonlinear term, the one we shown at the beginning, how this term, and for that matter, all the other terms will look like. And also something that we should have mentioned is that by assuming that the velocity z, it does not depend on the z direction, we automatically satisfy this condition, as we will see next. So let's find it out. Basically here, this is the multiplication of this matrix whose components are 0, 0. The partial, the derivative is no longer partial. Now this is a total derivative of this matrix multiplying this vector 0, 0, bc. Okay? It's easy to see that this will be, every single term of this vector will be 0. Okay? Therefore, we can say that, therefore, our equations become so the equations become, on the left-hand side, we will now have 0, because remember, we said that this is steady state flow, and we also just proven that this term is 0, so nothing survives on the left. On the right, we have mu times the Laplacian, and the Laplacian we now know is this, right? Is these derivatives, the two of them. Everything else is 0. Then we have minus the pressure gradient, which in polar coordinate, in cylindrical coordinates, looks like this. And nothing else, because as we said before, we're not considering the body forces on the problem. Doing it that way, then, in a similar way as we did for this, the divergence is essentially the derivative with respect to r, BRB with respect to r, partial of the another term will be the, well, we don't even need to write this down. I should have said that before, because all we need to say is that the only term which should be taken into account is this, but we know that this velocity term does not depend on z, so that's 0. Okay? So that being said, we now see that the last equation, this one here, is automatically satisfied. So we don't need to do anything. We don't need to calculate anything else to enforce this conservation of mass. And this system of equations, the one coming from the first expression, could be written in the following way. So this could be essentially the pressure derivative with respect to R0. The derivative of the pressure with respect to theta 0. And the last one that says mu times the second derivative of the velocity plus this term that comes from the cylindrical coordinate system. That should be equal to the pressure gradient with respect to C. Okay? The pressure, which is a scalar function, having these two pressure derivatives, these two partial derivatives being equal to 0, that implies that P as a function can only depend on Z, right? So that's the only variable in play for P, for the pressure gradient. On the other hand, if you recall, we said that the velocity is a function of the radius, and here we have that pressure is a function of the position, the axial position. So the only way in which this inequality could be held true is if that's equal to some constant value. Okay? Or put it in other words, for this equation to hold, we need to enforce. So we essentially said we need to enforce the condition that says that the pressure gradient is a real number, is some given number. It could be positive or negative, and in fact, the sign of this number will tell us if the fluid is flowing in one direction or in the other. And that's very simple to check. If we do a very simple plot where we have the axial position Z on the horizontal axis and the pressure as a function of Z on the vertical axis, what this is essentially saying is that the pressure gradient being a number means that if you take 2 points on the axial direction of the pipe, say point Z1 and point Z2, the curve defining this will be a straight line like this. Okay? So basically saying that here, for instance, this would be the pressure at point Z1, which we can call P1, and this would be the pressure at point P2. Okay? So that basically say that the pressure gradient, the pressure as a function is a linear function, right? Depends linearly on the Z direction. And since we're only interested in the pressure gradient, in theory, our pressure gradient could be a parallel curve like this, right? Up or down, okay? We don't really care. As long as this is a straight line with the same slope, the values of the pressures themselves don't matter. What matters is the pressure difference, right? So if that being the case, we can now write the last equation here in the following way. So we'll say that this is the second derivative with respect to r of the velocity, the axial velocity term, plus 1 over r, the first derivative here, that's now 1 over mu, the partial derivative of p with respect to z. Okay? Knowing now that the right-hand side is a number, which is known because in theory, we always know the viscosity of the material and the pressure gradient, all right? Then for integration, as you can see, this is a second order differential equation, right? So we can solve this, and from the solution of this, we'll find that there's two constants of integration, which we'll see, as we will see next, that are easily found. What I'm going to do now is a small trick and say that this left-hand side of this equation could be written as this instead, okay? And that's equal again to 1 over mu, the partial with respect to P, of P with respect to C. So what did I use here was basically the fact that if I take 1 over r, the partial with respect to r of r, the derivative of the velocity with respect to z, that's equal to, that's going to be the derivative of the product rule. So it's 1 over r multiplying. The derivative of this is 1 times the second is this function here, plus the first times the derivative of the second. Okay? And that essentially means that if you multiply this or distribute this factor on both, we'll essentially have 1 over r dv dr plus these two r's cancel each other out. And we now have the second derivative with respect to r, which is basically what we had in the first place. So this is now a very simple equation, which we can write down as ddr r dv c dr equals 1 over mu the partial, which is again, remember, is a constant, times r. Integrating directly, we find that this is r, the derivative, equals, this will be now 1 over mu, the partial derivative. Now this is r squared over 2 plus a first integration constant. All right? Okay, so that means that the solution is very easy to find because now we're just one integration left from it. If we divide this by the radius again, we will see that this is the derivative of the BC with respect to the radius is now 1 over mu. This is the same term, but now instead of r squared, now this is r over 2, and this becomes c1 over r. So before we continue, it's important to analyze the derivative here. We are looking for a solution that works for any value r, which is between 0 and the radius of the pipe, right? But what happens if we evaluate this at 0? Essentially, we have something like C1, which is any number, any real number, divided by 0. As you may probably know, dividing by 0 is basically not allowed. This term is going to blow up as we get closer and closer to 0. So what does that mean is that since we're looking for solutions that are well behaved at the origin, because that's the only point where this thing doesn't work. Origin meaning that when the radius is 0, that means that we need to enforce C1 to be 0. Okay, so there's no other choice but to choose C1 as 0. That being the case means that our differential equation is now this. Okay, it's just 1 over mu, the partial times r over 2. So finally, the final integration will give us the solution we're looking for as 1 over mu, the partial with respect to z, r squared over 4 plus a new constant we can call z2. And the final step, because again, we have an integration constant, is precisely the non-slip condition, right? We essentially say that the velocity evaluated at the outer radius, the radius of the pipe, must be 0. As again, this is considered as the non-slip condition. So that implies that if we evaluate the solution at the radius of the pipe, we essentially obtain this, right? We just switch from lowercase to uppercase r, and that must be 0. So if we solve C2, for C2, the right-hand side, we'll see that C2 is just negative 1 over mu. Let me put it that way, PDZ, r squared over 4. Finally, that implies that C2, the value of C2 in the solution is essentially meaning that the equation we're looking for is I'm gonna write it down slightly different. I'm gonna take this 4 and put it in the same factor here. So it's 4 mu. The partial derivative, which you remember again is a constant, r squared, and now I'm gonna do the same here. So we have the exact same terms, except that this one is with capital R. So taking a common factor on both sides give us that this is 1 over 4 mu the partial derivative times r squared minus r squared. And this is basically the general solution, which we know as the Hagen-Poiseuille flow, solution for a Newtonian fluid flowing on inside a pipe. The only final comment that we should make, which is usually done as one of the assumptions, but it's not really assumption, it's rather a consequence of the solution, is that this solution works only on fully developed flows. Okay? So what this is essentially saying is that this is the solution that ultimately, like is this last solution that you'll see if this is a very, very long pipe. If you take in consideration a very long pipe like this, where in this point, in theory, the flow is at rest. Let's say that this is a part of a container, like a very giant container. And then flow is, the water is flowing just because of the pressure gradient. That means that the solution will evolve from something like a flat part in the center, like we can see in here. Downstream, we will find the parabolic profile we just found. Okay? So this is basically how the solution is found. Once you have the solution, it's very easy now to calculate the volumetric flow rate and all the different features of the fluid, which are typically given in textbooks. So that's all for now, and thank you for watching.